Hi, everyone. My name is Rose Yu. I'm assistant professor at the computer science department at the UC San Diego. So today I'll briefly talk about one of our recent works on physics-guided deep learning for COVID-19 forecasting. So our team is one of the official CDC forecasting teams. And this is a screenshot of national forecast on the CDC website. So our team here, UCSD and EU, consists of different experts from very diverse areas, including grad students from UC San Diego, collaborators at UCSD Data Science Institute, the collaborators from epidemiology, Xingyue, Mateo, and Alessandro Vespiani from Northeastern. So let me just briefly talk about what is the details of our model. So typically when we think about using deep learning to forecast time series, the to-go method is a recurrent neural network or an RNN. So in this case, I'm showing you a picture of an RNN in a sequence-to-sequence architecture. So a sequence-to-sequence model has an encoder that takes the historical observations from a time series, in this case, x0 to xt, and it has the decoder that generates the predictions, xt plus 1 up to xt plus h. So in a mathematical formula, an RNN is a nonlinear dynamic system. Given the input, xt, it maps the input into a hidden state through a nonlinear activation function, f. And then output, y, is another nonlinear function of the hidden state, ht. So note that here in RNN, it only models the temporal dynamics in a time series. However, for forecasting COVID-19, because there exists strong spatial patterns in terms of people's commute, travel, and air flights, there's an urgent need to model the spatial dependencies in the data. And that is a key contribution of this model. So the model draws from our previous research on traffic forecasting. So typically when we model spatial dependencies from an image, we can think of an image as pixels distributed on a regular grid, and we can model the spatial dependency in an image with a convolutional neural network. However, when we think about the epidemic diffusion transmission, we're modeling the state spatial dependencies on the irregular grid. So in this work, we make an analogy that the epidemic can be thought as a diffusion process on an irregular grid or a graph. In this case, the nodes in the graph represent different states or different counties. And then the edges between the graph nodes represent their mobility statistics. We can calculate the mobility statistics using the travel patterns such as commuting and air networks. We developed a new type of convolutional operator called diffusion convolution to model the spatial dependencies on the graph. The details of this model is published in a paper in 2018. So in a nutshell, diffusion convolution takes the adjacency matrix, which represent the graph. So each element in this adjacency matrix, Aij, is a function of the distance between two nodes, Vi and Vj. So in COVID-19 application, we calibrate the distance between two nodes or two states using their mobility statistics. Given the adjacency matrix, we can calculate the in degree and out degree matrix, which is the row sum and the column sum of this adjacency matrix. So we took inspiration from a very classic graph theoretical results to characterize the dynamics underneath the diffusion process. So this theoretical result states that the stationary distribution of the diffusion process can be represented as weighted combination of infinite random walks. So a random walk can be represented as a random walk matrix, which is the operator here, d minus 1 times adjacency matrix A. We can raise it to different powers. Let's say if we raise it to the kth power, it represents a diffusion process propagate on a graph for k timestamps. And then there's a coefficient in front of it, theta. This represents the speed of the diffusion at different timestamps. So this result comes from graph theory. In order to integrate this operator into a deep neural network, we simply replace the weights theta with trainable coefficients in the neural network. So that is the equation shown in the bottom here. We have trainable weights theta O representing the out degree diffusion and theta I representing the in degree diffusion. And then we pre-compute the random walk matrix D minus 1A for both the out degree and the in degree diffusion. So the theta represent the weights in the neural network, and we can learn these weights using backpropagation. The input here, xt, represent the features at timestamp t. So for COVID-19, the features can be the total number of hospitalization, total number of infections, or death numbers at different states at a particular time. So in the graph, we can visualize this diffusion process. So imagine the virus concentrate at a particular location, starting from the center nodes. So here, the center node has the highest density, representing the original patient 0 geographic location. A diffusion process models the transmission dynamics of viruses. So according to this dynamic, the density of the disease diffuses into multiple timestamps. So here we are visualizing the k-step diffusion. The disease transmits to the closest neighbors and then to the second hop neighbors and so on and so forth. So based on this intuition, we can make modifications to the previous recurrent neural network architecture by simultaneously modeling both the temporal and spatial dependency. So just from the previous slides, we know that an RNN is a nonlinear dynamical system. It maps the input states xt into a hidden state ht, and then the prediction or also the state at the next timestamp is a function of the hidden state ht. So to incorporate temporal dependency, spatial dependency, using diffusion convolution, we can simply replace the matrix multiplication operators between the weights w and the feature x with a graph convolution operator that we defined before. So in this way, we can model both the spatial and temporal dependency in the COVID-19 time series. So another drawback of this model is that it is a deterministic system, which means there is no confidence interval associated with our prediction. So in order to satisfy the probabilistic forecasting requirement for COVID-19, we use some techniques from uncertainty quantification to quantify the forecasting uncertainty of COVID-19. In this case, we adopted several different techniques. One of them is called quanti-regression. So this is a frequentist method to quantify the uncertainty in time series. Essentially, given a prediction y, quanti-regression slightly modify the loss function of our model from the previous mean absolute error between the ground truth y and the predicted y hat into a pinball loss. So this pinball loss function basically is a piecewise function showing on the right-hand side of the slide. Whenever the difference between the ground truth and the prediction is positive, then we multiply it by the threshold tau. Whenever the difference is negative, then we multiply by tau minus 1. So in this case, it generates the confidence interval directly through minimization. Another technique is a Bayesian technique for quantifying the forecasting uncertainty. This is known as Monte Carlo dropout. It utilizes the fact by randomly dropping out the weights in a neural network, we can mimic the stochastic in the system. So in this case, given a standard neural network, we can apply a dropout by simply zero out some of the neurons in this neural network according to a certain probability. And this probability is associated with the confidence interval that we want in the final forecast. So far I've talked deep learning for COVID-19 forecast. And the title of this talk is about physics-guided deep learning for COVID-19. So let's first look at using deep learning for forecasting COVID-19. This is a benchmark study for various deep learning models, including our own, for COVID-19 in the past 3 weeks. And we forecast the infectious, recovered, and the death number. We can see that compared with the traditional neural ODE-based methods, which are mechanistic models, including the SEIR, deep learning models are actually not significantly better than the traditional mechanistic models in forecasting the infectious and death number. This is because for COVID-19 application, the number of examples that we see is very small. So deep learning models work very well for large data. They suffer from small data issue. And this issue is very common among life science applications, including the COVID-19 forecasting. So the key insights that we gain in working on this project is that we need to combine the first principled physics-based models with deep learning methods to tackle the small data issue. And our physics-based models is research done by our collaborators called GLEAM. So GLEAM stands for Global Epidemic and Mobility Model. It's a mechanistic model that combines real-world data on populations and human mobility. It uses stochastic differential equations to describe the disease. So we evaluated on 2 metrics. One is on the mean absolute error for forecasting accuracy. The other one is on the uncertainty using mean interval score. The mean interval score is that it covers the interval of the forecasting using a score function, and it does not require full predictive distribution. So it's a good fit for deep learning forecast. It's also easy to compute. We can directly plug this loss function into the optimization objective of the deep learning model. So here is the comparison of the forecasting accuracy for a deep learning model, the GLEAM model, and the hybrid model, Deep GLEAM. So we look at the mean absolute error for 3 weeks ahead forecasting. You see that by only using deep learning model, the error for forecasting COVID-19 is very high. However, if we combine the GLEAM model and the deep learning model, we have the best performance among all the models. If we look at the actual predictions from all the compare with the ground truth, this is for the forecast in California. The solid line represents the ground truth, and then the orange line is the predictions from Deep GLEAM. So you can see that Deep GLEAM model follows the ground truth closely compared with other models, whereas the pure deep learning method, which is the dashed line, blue dashed line here, only captures the trends in this time series of weekly deaths, the nuanced stochasticity in this time series. This also highlights the importance of incorporating physics-guided for this particular applications. And you can also look at our real-time forecast on this website at datascience.ucsd.edu/COVID-19. We update our forecast daily, and this is a visualization of the probabilistic forecast from our model with 2 different types of uncertainty quantification techniques. The ground truth is a solid line here, and then the dash, the red interval is the forecast using quantile regression, the blue line is a Bayesian type of Bayesian uncertainty quantification techniques. Here we're showing the forecast for US as well as different states. So that's all I want to talk about for this talk. I would like to thank all the sponsors for the research in my lab. And then if you have any questions, you can find my contacts on my website, as you can also follow me on Twitter. Thank you very much.